Okay. I think we can start. Good morning and welcome everyone to this new season of Astromeeting. I take the occasion to welcome also the new member of the LOC, which are Viola Allevato, Maria Rita Murabito, and Eleonora Fiorellino, that this year will join the LOC of Astromeeting. Today's speaker is Elena Bannikova. Elena is a professor of the Astronomy Department and School of Physics at Kharkiv National University, and she is a leading researcher of the Institute of Radio Astronomy, National Academy of Science of Ukraine. Due to the war, Elena is here with us at the Observatory of Capodimonte, and her research field is dynamics of gravitating systems, AGN ring galaxies, gravitational lensing, vortex hydrodynamics in analytic approach. So I would leave her the floor for her talk.
Thank you. Can you ask if they can see the screen mount, the full screen mount?
Yes. Are you all able to see the screen? The presentation?
Yes.
Okay.
Yeah, see, yeah, okay.
So okay, I need to use this here.
So I will, in my talk, I will speak about gravitational properties of toroidal structure. I choose some of the work which I think can be interesting related with the subject. In the beginning, I would like to show my university. So now this building is one of the main buildings, the second one like this, without windows now. And we are proud that Lev Landau was lecturing in Kharkiv University, and the idea to write this course, famous course, came exactly to him in Kharkiv University. And Alexander Lipunov, who is famous with investigation of stability of the system. So why toroidal structure? Really, we know some object which has a ring or toroidal structure. As an example, this is ring galaxy, beautiful object known Hawke object. This is dusty Tori in AGN. Also it can be, for example, appearing of ring of dark matter when you have two collisional systems. And for me, it was even surprised that our work about gravitational potential was used in a review of Bennu asteroid, because Bennu asteroid has an interesting shape. There is about like a ring, so you can see here. And okay, I don't see pointer here. One of the ideas, if you would like to know to calculate the precise gravitational potential, you need to know potential of the ring. This is particular case of the torus. This is content. It's look a lot, so I will try to join in short time these points. And I choose for this talk four 4 points. This is gravitational potential. They name it some things with dynamics in like galaxies, gravitational lensing, and what we are doing just now, this is our model simulation of clumpy torus and EGF. And you can see that about this I will speak much more. So when we, in principle, in the beginning, we wanted to simulate the torus, but we discovered that something strange, and we understood that we need to investigate gravitational potential of the torus. Why? Because it's strange, but potential of the torus haven't been investigated at all. And here you can see the work, the citing the work Bernhard Riemann about potential of the torus, where he just suggested that potential of the torus can be considered as a Fourier series. It was one of the last his work. So, and we decided to investigate it, and we considered it even much more simple case, because even this case was not investigated. A homogeneous circular torus. Why new approach? It's understandable, of course, that you can obtain the potential of body, some complicated shape, just a direct integration. But sometimes this doesn't tell you some information about property of the gravitational property of this body. So new idea, it means that we decided to obtain the potential of the torus, consist the torus of the set of massive circle. This idea, like idea of Newton, maybe he used exactly like this when he consists to obtain the potential of the solid sphere. He used the potential of spheres, I think this in spheres. So, and you can see here the location of massive circle parallel to the equatorial torus plane. It's also understandable why we use a massive circle, because this is limited case when main radius of the torus come to 0. So we have a massive circle. Finally, this is, you can see a new expression for torus potential in this case. And this is not friendly expression, because it's a double integrating from elliptical integral. And I can tell that rho et zeta, this is dimensionless coordinates, radial and cylindrical coordinates. So this expression doesn't tell us anything about properties of the torus. But we decided in the beginning to numerically to compare the potential torus of the torus with the potential of massive circle. Here you can see this is in blue, so I don't have a pointer, I can show the participants remote. You can see blue, this is potential curves of the torus with different thickness, with a different, as we say, geometrical parameters. So geometrical parameters, this is ratio of the main radius to the major. And you can see that, and the red curve, this is potential of massive circle. So you can see that potential curves of the torus with a different thickness described in the potential of the massive circle. And it means that external potential, now I speak about external potential of the torus can be represented with good accuracy by potential of massive circle. Of course, we discovered this numerically, but after this, we prove this analytically. And here you can see one of the formula, which really much more simple than formula which I showed before. And you can see here the potential of the torus. This is potential of the massive circle in this red circle, and some multiplier which consists of the geometrical parameter of the torus, the thickness of the torus. Of course, you can see here some analogy with the famous Newton result for the solid sphere and the massive point. So we know that external potential of the solid sphere exactly equals potential of massive point. With the torus, this is like this. So the external potential of the torus almost equals the potential of massive circle. Why not exact? Because torus is more complicated body, and the Gaussian curvature of the torus depend on the angle in cross section. So in outer part here, The curvature is positive, inside negative, and in 2 points equals 0. But it's understandable that this result allow us instead to consider the potential, complicate potential of the torus, if you would like to investigate the dynamics in outer potential, to use just the potential of massive circle. This is, of course, beautifully, because it can simplify some problems and also can allow to obtain some analytical solution. Also, in this paper, we investigate inner potential, which is also interesting because we could see in this complicate potential of the torus, the potential of the cylinder. But I would like to jump in the next subject, the work about structure of orbits in Hawk-like objects. So you can see it's a beautiful object with a central galaxy and the ring of star formation. And in this galaxy, this ring of star formation, the mass of this ring is comparable with the mass of the central galaxy. So, and the idea was investigate if we have Hawk-like object, I call the object which has a mass, the central mass, and the massive ring around. Now let's try to understand what it will be in such a kind of system. So since ring, or torus, in this case ring, has an attractive body, so the gravitational forces will act on the particle in the system such a way that from one point it will be acting of the forces from the central mass and from the ring. And as a result, we will have some geometrical locus where there is a balance of these forces. So we decided to call this, this locus Lagrangian circle in analogy with Lagrangian point L1 in three-body problem. And here you can see that we even could obtain the equation for to obtain the radius of Lagrangian circle, which is enough beautiful from mathematical point of view, and since that it's joined two elliptical integrals of two kinds through the number p. And what is important that using this previous obtained result about gravitational potential, we can even to find the equation in algebraic form. So what is interesting in this problem also? So it's understandable that I will jump back because I would like to explain that it's understandable that particles inside Lagrangian circle, this is inside red circle, will belong to central mass in sense of contour of the gravitational forces. When I decided to put the particle on circle orbits inside this region, I discovered something strange that I can find the circle orbits up to some radius, but starting from some radius far from the central mass, the particle doesn't want to move in circle orbits. And if you will look on effective potential, you will understand why. So this is effective potential of the system central mass in the ring. And you can see for different value of momentum of the particle. So you can see that there is a minimum which correspond to stable orbit and maximum which correspond to unstable orbit. When moment increase, we can see that finally the minimum and maximum merge with each other, and this is exactly correspond to the radius of the last stable circular orbit in this problem. What is interesting is that this is similar to the relativistic case. You can see here example. But otherwise, there is a maximum nearby black hole and minimum far from black hole. And for some moment, minimum and maximum merge with each other. And relativistic case, this last stable orbit called in relativistic case most stable circular orbit, ISO. So I decided to call this orbit the outermost stable circular orbit. Again, we can obtain not complicate equation to obtain the radius of this object, again due to the previous result. Here you can see some analogy with the OSCO and OSCO in relativistic case. So I can tell that the stable circular orbit exists in such a kind of system inside OSCO, and for relativistic case outside. So, but there is this interesting analogy. And it's understandable that, so discovered that between Lagrangian circle and the last outermost stable circular orbit, we will have some region where particles or stars, if you consider them as stars, can't move in circular orbits. So they move on more complicated orbits. And due to this, they will connect with each other to change their orbits and throw out from this region. And as a result, it will be gap in distribution, in star distribution. This looks like a Kirkwood gap in asteroid belt. So the mechanism is the same in the sense that when asteroid came in this region, the asteroid changed the orbital elements and go out from this region. The mechanism is the same, but the nature different, because in Kirkwood gap we have a deal with gravitational resonance and influence of Jupiter. Here, this is direct contour between the gravitational forces from the central mass and from the ring. And if we just calculate the width of this gap, for example, for Hawk object, it will be approximately 3 kiloparsec, which if to put this, simply to put this in this picture, it looks like this. The next work which I would like to mention is this talk. This is gravitational lensing effect on the system. When gravitational lens looks like this, I put here a object. So it means that central mass and the disk with the hole. Now, to be honest, in the beginning, we decided to look what it will be if the gravitational lens will be like this. And we simply distributed 500 masses, gravitating masses with that central mass. We look at this and understood nothing because it was something strange. 1 engineering, 2 engineering, 3 engineering, we changed parameters. We even discovered that it can be 2, for example, arcs and 5 images. So it was a mess. And why we decided to simplify this problem? Because when you simplify the problem, you can find basically result effect, and after this you can make the system more complete. So we consider the problem with a lens, which is a central mass, and a homogeneous disk. Without central mass, this problem a little bit was touched by Schneider, but we put also the central mass. We made this a little bit complex in the sense that we put not one source, but the set of Gaussian sources like this, 15 and 15 feet. And here you can see the lens equation for the system for surface density, which can depend on the, can have some law. But finally, we even put the surface density constant. So why? Because for this case, this integral we can take. And we can, in principle, to understand what's happening in such a kind of system. What we discovered, you can see here, that in this system can be 3 Einstein rings. So here the red circles, this is boundary of the disk lens, of lens disk. You can see here 3 Einstein rings. You can see here 2 Einstein rings. And you can see here that 1 Einstein ring is even more wide than another one. And here 1 Einstein ring. Also interesting that in this system we have not only images like arcs, but also radially elongated images, which appeared on the disk. We analytically solved this problem, so in the sense that we understood when we can see 1 Einstein rings, 2 or 3. I will show on this slide. can see Einstein rings in sense that the second Einstein ring which appears in disk can really form for this equation. If you look on the parameters, so we are in this field. As soon as we change the surface density in the disk, and this is less than this critical value, so we will have only one Einstein ring. And we are exactly in this field of the parameters. Parameters, this is radius of the second Einstein ring, second we call, which form on the disk length. And we are in the field of the parameter when the second Einstein disk can't be formed. This is interesting because in principle, if you have length with a central mass and the ring structure, for example, you can see this ring structure in any band, this length can looks like a point mass. So to product one Einstein ring. Okay, now I would like to speak about finally about dusty theory in active galactic nuclei, which for now, for us, we are working with this with our model. And I would like to remind the structure of active galactic nuclei, such a way as it's supermassive black hole, of course, accretion disk, so jets, and the dusty toroidal structure. And I put here external accretion, which really we can see that there is external accretion in AGN, and sometimes it's important because it gives a matter to the torus to live for him for a long time. Here you can see unified schema, idea about the presence of the torus toroidal structure in AGN appeared many years ago. And because we have Sept 1, Sept 2 galaxy, radio loud galaxy, this is quasars, radio galaxy, blazars, so on. And in this scheme, the differences between type 1, type 2 AGN can be explained by different orientation of the torus relative to an observer. So if you look on some angle, we can see accretion disk, and this is Sept 1. Or for radio loud for galaxies, this is quasar. If torus block the emission of accretion disk, we look in this direction. This is Sept 2, or this is radio galaxy. And immediately it was understandable that torus should be geometrically sick to explain statistical data. And I will show that it was proved by direct observation of such a kind of object. Immediately, of course, there was a main equation about this clumpy torus, toroidal structure, because it was not understandable. This is clumpy or continuum medium. This is to explain how the torus can have Donut shape. Why is the torus geometrically sick? Because it looks like if you have a disk of continuum medium, this structure should be stretched along the radial scale and create the disk. The mass of the torus, again, the question about clumpy or continuous medium, dynamics in the torus, of course, the question about formation. All of this question was investigated using not only theoretical point of view, but also observations in different bands. And I will speak a little about this. The first, this is mega maser mission, which started to investigate in such a kind of object in 1996. It was the first works. And here you can see a famous object, AGC 1068. This is such kind of canonical object because it's not far from us. And here you can see the mega masers. This is water mega masers. And we immediately understand that since this is water mega masers, it means to create this emission, you need to have to have a collisional pumping. It means that you need to have shock waves. So, and one of the suggestions was that this mega maser appeared in the boundary between the wind in AGN and throat of the torus. You can see also blue and red. which understandable that there is orbital motion, but there is a symmetry because just a few mega major spots in blue and the line in red. So not completely understandable. This is, for example, part is a throat of the torus, so I can write here, like this, or this line of the mega majors in equatorial plane. And this observation also, this, and I put only one picture, but it was independent VLA, VLBI observations, also showed that the structure should be clumpy because there is a dispersion of velocity in this mega major emission. It was important to obtain observation in infrared band. It was made on VLT for the same galaxy. And it was, as you can see, the first direct observation of obscuring torus. In this galaxy, we showed that really the torus is geometrically thick. And there is a stratification in temperature. So we have a hot component in the center and a warm component of temperature around. One of the suggestions was that this hot part of the torus, this is throat of the torus, which heated by the emission from the accretion disk. And the warm component, this is torus body. Of course, there is a question, but how we can see this hot component, which is inside of the torus, so and the clouds is optically thick. One of the explanations can be situations that we have a clumpy structure and part of the emission penetrates through the torus body. The second answer is that it can be some orientation of the torus such a way that we can see the throat of the torus. And I will speak about this later. Here, this slide shows the different models, radiation transfer, which showed radiation transfer problem for the torus and comparison with the spectral energy distribution in observational spectral energy distribution. And now we are sure that the structure in the torus should be clumpy. We even can say that, when I say we, I mean as the people who are working in this field, how many clouds should be in the equatorial plane. It's approximately 10 clouds. And on the sum line, it should be like on 45 degrees, it should be like one cloud to satisfy the obscuration condition. Of course, the important step was made with ALMA. Again, I showed the first discovery in millimeter band of the torus in GC 1068. So, which was discovered again the thickness of the torus. You can see orbital motion. And what is important that was obtained also observational data not for one or two galaxies, but before one or two Sept galaxies is before. For example, for GC 1068 and for Circinus. It was obtained the maps of velocity distribution and velocity dispersion distribution for 6 galaxies. So now we have much more data. And velocity distribution allow us to understand the dynamics in such a kind of object. This is also a beautiful result. This is torus in Cygnus A, very famous object, with jets. And in the center, this is a density map of the torus in central engine. The mass, of course, the scale of the torus, for example, for Sept galaxies, this is like a parsec scales, 5 or 10 parsecs. In the case of this radio galaxy, this is, you can see 200 parsec, because the mass of black hole is a huge comparison with the Sept galaxy. So to summarize what I said shortly about the observational data, what we know about torus, that this is geometrically thick. The mass of the torus from 1% to 10% of the mass of supermassive black hole. maybe even more, but what we can estimate for now. But it means that the self-gravity of the torus must work. And also, for example, rotation curve from the ground of Maser mission showed that there is a non-Keplerian motion in the torus. Also, what is important that in Seyfert-2 galaxy, when the central engine hidden by the torus, it's complicated to estimate the mass of supermassive black hole. Direct estimation you can make exactly investigate the dynamics around it. So, we decided to work with this and to build some dynamical model, which take into account observational properties, observational data. Of course, Zora didn't say about these models with hydrodynamical models of the torus, but we simulate our torus considered this is a clumpy structure. So we consider it like in bodies, considering body simulation. This is our team, I would like to say, and you can see that now we are in different places. Nina, she is my former student, now she is PhD student at Padova. With Vladimir, we came during the war in Italy, and thanks all colleagues and here for me in Capodimonte, Marcella, Marilena, Enrica, that helped me to continue this work here. So what we are doing, we consider in-body simulation of the torus, and we made many, in principle, we made many simulations for different mass of the torus, comparison to the mass of the central mass of the supermassive black hole, from 1% to 10% of supermassive black hole mass. We put 100,000 particles, and each particle we consider like a cloud because we use a Plummer potential here. And we try to find the equilibrium state of this torus. So we found. Now before we use more simple algorithm, now we're using both of our team, this high order Hermite integration with GPU. 100,000 clouds, it's enough. So of course we could put much more. We have enough possibility to simulate with a much larger number of the particles, but we don't need it because exactly for obscuration condition we need such a kind of number of clouds. This is for now I will show the result for this initial condition when the clouds has orbital elements such a way that they distributed randomly in Keplerian elements with some anisotropy in two directions which mimic the role of the wind. Because this is simply a simple way to represent the possible formation of the torus. Such a way that, for example, we can suggest that in the beginning we have a black hole with the clouds around, which move just randomly with random distribution of orbital elements, the same like in the center of our galaxy. And the beginning of active stage, it means that the equation disk became much more powerful, so we have a wind. And in this region, the cloud, due to presence of emission from accretion disk, throw out from these cones. The clouds which are in these places, due to the fact the clouds are optically thick, they continue to move, and finally this toroidal structure can form and obtain some equilibrium state. We made this embodied simulation. We made it for different number of clouds. I show here you can see from 8,000 to 100,000 as an example. And we can see that finally the system in real state, so it's an equilibrium state. And it's this interesting that you can see how the shape of the torus changed due to the beginning of the simulation. Here you can see this is initial condition, the central mass here, and this is the cross section. We built it such a way that we all clouds gathered in one plane, which is perpendicular to equatorial plane. And you can see that in some interval of dynamical time, the torus change, but finally the cross section of the torus is geometrically simple and even have some elliptical shape side is a core. What we also can see is that the motion of clouds in the torus is not complicated. This is not like in Keplerian disk. So, and for example, in outer part of the torus here, the cloud will move with velocity which is less than Keplerian velocity for some value of the central mass. Here, clouds will move with more higher velocity near to the central mass. And in the center, this velocity, which would be approximately Keplerian. Keplerian in the sense that if we calculate Keplerian velocity for the chosen value of the mass. I'm not sure that this video will work, maybe not. So I will not push this video to. In this video, you could see the example of onboard simulation and the dispersion of velocity in the torus. So what about it? Okay, it's working. Miracle. Okay, so you can see here that here the clouds move more fast, and here in this cross section you can see, and here slowly. And what this can say us, if, for example, you observe the clouds from this side, you obtain the velocity, and you want to estimate the mass of supermassive black hole in the center, you can make a mistake if you will consider it like a Keplerian disk. So, because the velocity here will be less than in Keplerian disk. Okay, okay. Okay, time. Here I would like to show you our simulation of, I would like to say, ALMA map, some theoretical map, which can mimic ALMA map. What we are doing? The first, we are doing an body simulation. After this, we rotate the torus relative to an object. After this, we divide the picture plane on some cells, some grid, to mimic ALMA resolution. And we using ray tracing from the observer. So the rays go from observer to the cloud. And when we meet cloud, so we use the corresponding velocity. So we take into account the points the clouds obscure each other in this case. And now, after this, we calculate the mean velocity in each cell. And here you can see some model maps of velocity and dispersion here below. For example, and of course, we understand the parameters. This is the scale of the cloud in this case too, because the clouds obscure each other. So here you can see the simulation, our simulation for GC 1068. And ALMA observation of the torus in GC 1068. So you can see that this looks similar. And we could obtain to estimate the mass of supermassive black hole, taking into account all these effects, which this is 5 multiplying 10 upon 6 solar masses. For example, this is higher than the mass, if you will obtain the mass, considering in simple Keplerian motion, which it was made in this paper. Also, we decided to apply our model to other galaxies, Sept galaxies. So here's the dispersion velocity map, velocity dispersion map here. And we can see that there is a high dispersion in the center of this map, which also you can see here on observational maps that there is an external accretion here, for example. And here you can see our map. So we can see the central part in our simulation, which has a high dispersion. What is this? This is exactly the throat of the torus, which we can see due to orientation of the torus relative to an observer. So, and finally, we obtain the parameters of these galaxies, the mass of black holes, and the scale of the clouds. This is relative scale of the clouds, normalized on the major radius of the torus, and orientation of the torus relative to an observer. In principle, these two parameters, they are coincide with each other. We need to consider it together: orientation and the scale of the clouds. Also, we so I have 5 minutes. We decided to compare our ALMA maps with the temperature distribution maps. With this, we use semi-analytical model. So in the beginning, we found analytical expression for temperature of the cloud, suggestions that the clouds and the accretion disk are in thermodynamical equilibrium. In this case, and also we put some simplification. So we understand that the profile of temperature of accretion disk correspond to Shakura-Syunaev model, so we can see it here. But we show that if we will consider the accretion disk with some effective radius equal 10 gravitational radius, the amount of energy will be the same as for Shakura-Syunaev accretion disk. And it allows us to obtain this formula. This is temperature of the clouds, this is accretion rate of the gas in the accretion disk, and this is distance from the black hole. The function f showed us anisotropy of emission of accretion disk because accretion disk can obscure themselves. And finally, you can see here our model maps of temperature distribution for different scale of the cloud. You can see here the throat of the torus, which heated by emission from accretion disk, and the temperature, which we can calculate due to our formula, is approximately 800 Kelvin, which corresponds exactly to the observation of VLT. And if we would like to interpret, for example, like this map, so we understand that it can correspond to this case or to this case. So we can obtain the parameter of the torus orientation relative to an observer. And the final point, I very quickly understand that I have a little time. I would like to mention our recent result about counter-rotation in the torus of GC1068. It was really unexpected results obtained by ALMA. That it looks like torus in this galaxy. Here you can see map, has a one direction of rotation, so you can blue and red, and opposite direction of rotation inside. Also, you can see here mother spots, which red here, but blue part here, and a little bit blue here and red here. Also, you can see here the continuum emission in the torus, which has an X shape, and which can tell us about the emission of the torus throat, possible. And it's understandable that if you have a medium with two layers which move in opposite direction, finally you will have instability, the Boltz instability, and the system will collapse. So it's impossible. One of the suggestions was that this is influence of the wind, like this. So this is some sketch, and we decided to check it. Now this work we already sent to journal. We considered our body simulation with all this procedure, but we also add the wind, but asymmetrical wind, because we need to obtain something asymmetrical in distribution of the cloud. Asymmetrical, it means that the axis of the wind does not correspond with the axis of symmetry of the torus. So it's titled on some angle gamma. And wind we consider here as infrared emission, which is related with accretion disk. So here you can see the formula, and we calculated that the power of the wind is enough to push out the clouds. We put it in our simulation, and here you can see effect. So for different relative radiuses of the cloud, this is larger cloud, this is less cloud. So we can see some effect of counter-rotation here and here. And for some orientation of the torus relative to an observer. So in this procedure, we use ray tracing twice from the operation disk to the clouds, to choose clouds which are under influence of the wind. And the second, ray tracing from the observer to the torus. And we can say that this counter-rotation can be apparent counter-rotation, but not real, due to orientation effect and the influence of the wind. And one of the last result, yes, it's if you will look on the shape of the torus rod, it has a X shape, and the distribution of high velocity measures, the clouds which can be responsible for the measure emission, you can see here a symmetry. So really there is one red clouds from one side and just even maybe not from another side. So this is a conclusion. I will not repeat. I just would like to say about open questions, which is a lot. And now investigators are working with the potential of the torus, and it's interesting to investigate elliptical potential of the torus with elliptical cross-section. Of course, not all understandable in dynamics in Hawk-like object. And gravitational lensing, of course, you can put non-homogeneous distribution on the disk. About AGN, just now we simulate binary black hole, and we try to, in sense, to understand can a binary supermassive black hole to do some influence, additional influence on the torus rod. So, and of course, we plan with external accretion, dissipation, and so on in our model. And I would like to finalize, just to represent our book, which we hope it will appear maybe in November or December. This is Foundations of Celestial Mechanics, which we finally finished. So, and I think it will be interesting for students. So thank you very much.
Thank you, Elena. Are there questions? Something from you. Yes. Yes, if you have questions, please switch on your microphones and make your question.
Vincenzo Antonuccio, can you make a question?
Yes.
Okay. I just would like to understand how do you treat. I mean, I saw in your numerical simulations, you seem to use only a Newtonian potential, even up down the central relativistic regions. Is this correct? And correctly?
Yes, yes. When we simulate the clumpy torus and AGN, we treat central mass, supermassive black hole as just a classical point mass, because we are far from the gravitational radius. This is like more than 1,000 gravitational radius. Yes, it's right. So we just put just a point mass.
Yeah, but at some point, for instance, in the derivation of the temperature profile, you use the accretion rate on the objects. I think a more sensible way of treating it would be to use, for instance, a Paczynski Vita potential, which simulates the effects of relativistic effects, at least in a Schwarzschild context.
Yes, sure. Thank you. I agree. But in this case, we consider it more simple problem, and since that we used the expression just for Shakura-Syniaev disk for temperature profile. Of course, if we would like to take into account relativistic case, relativistic effect, yes, I agree, we need to take into account these things. I guess. Because for temperature distribution, we just take the emission of accretion disk, the temperature of the accretion disk, what we need. And for this problem, for now, it's enough to use Shakura-Sunyaev disk. But maybe for some, to find some effects, maybe we can add something additional.
Okay. Viola, if you can come here.
So in one slide, you claim that the mass of the torus is from 1 to 10% of the mass of the central black hole. I didn't get if you found it like in your simulations or like observationally, and if it's valid just like, I don't know, at which redshift.
This is obtained from observation. So we can estimate the number of gas and number of dust in some cylinder along the line of sight. So in this case, we use observation data. If and this is like this. If, of course, but sometimes, for example, it was investigation of rotation curve and GC10 in other galaxies, which looks like that this rotation curve tell you that the mass of the torus should be comparable with the mass of supermassive black hole. So we don't say that it's impossible. We would like to say that we are now preparing the paper about the possible existence of the torus with a mass which is comparable with the central mass. Okay, I will be more precise, not with the supermassive, with the central mass, because we treat it like just a classical central mass. But for this, which I showed, this is observational data.
In the local unit.
This is a observation using Kalma and Will. So this is not so. But of course, maybe in future we can reach here.
Just ask a question, but it's close to the computer. Of course, my question is on the strong lensing part, of course. Of course, this is a very peculiar, very rare model. We expect that it's very, probably we can expect in a few cases in the real world, I guess. Or at least, no, at least for what we can expect. So I have two questions. One is, I have not seen the shape of the critical acoustic curves. I would be interested to know about that, since, of course, if you say that there are three Einstein rings, so the structures is complicated. Since knowing, of course, as you know, knowing the acoustic curve, we can know where to put the source.
Yes, we have, of course, acoustic.
This is interesting. Yes, typically, you know, when we have the most common lenses are the one with a single lens, and typically the structure is easy. So you have two sets of curves. One is the acoustic with the cuspid, and that is the one forming the rings. You know, the tangential arcs. So in case you can show me later, since I'm very interested to this. Another point is that I was starting from there. In the near future, we will go to discover 100,000 lenses. Okay, so with Euclid, we expect.
This is point. Maybe you will find strange rings.
Yeah,
if you will find it.
Yeah, that is my point. 100,000 potentially, 150,000. Have you estimated what is the fraction of this kind of lenses? Since we need to have a ring galaxy that is an extremely rare set of objects. Potentially, if it is phase-on, you have something, but if it is not phase-on, the model is probably more complicated.
But it's also interesting because this is not phase-on to look at the effects too.
Of course. Okay. But I don't know if you have estimated what is the fraction of these kinds of rare lenses within a rare class of objects.
We don't estimate it. Of course, this is not a huge number. It's understandable. But in any case, for example, I suspect that in future, and because the case for 2 Einstein rings, we know already one case with the 2 Einstein rings. So you can obtain it if you have 2 sources or 2-point lenses. Why not? We can, for example, by chance to see 3 Einstein rings, so like this. Of course, the fraction is not, this is rare, but rare objects are very interesting.
No,
in
in
this
fact,
case, yeah.
in fact, one of the
Because
school-
when the source, I don't remember the name of the source, with 2 Einstein rings, it's even much more rare, which
Yeah.
by chance,
No, of course. Yeah.
yes, it's more, but then, for example, in galaxy of some object with a ring structure due to
Yeah.
collision,
No, it look interesting, I guess.
And this is
so
only
far.
beginning because with my formal student, she's now in Heidelberg and she's busy with other investigation. But we made a simulation with non-homogeneous fields
Okay.
because it is homogeneous. But if you take real ring
No, of course.
and
it's,
then
substructures,
consider it like so, you will have some profile. And by chance, we can see that we can write great.
related total work. Right.
So yes.
Other questions? No? Okay, so let's thank Elena again. And see you next time with the Astromeeting. Thank you.
No, we are working with